this is a very, I think, simple talk or even trivial talk. But when it was asked if you had anything to say, I thought, well, maybe convex has something to do with connectivity, so I might as well propose something. It's also, you may want to ask questions, because the last referees report I received, they said you should get a native English speaker to correct things. So I don't know. So maybe you may not understand me. So this is a very simple problem that turns out to be even simpler than we thought. So I'm going to describe the problem, talk about the 1D case, which is trivial, and then look at the 2D case. And I'm interested, as usual, just in trying to find a polyhedral description. And then we'll see various ways of looking at it and how it gets simpler and simpler as you go along. Sorry, my pictures are not up to standard as usual. But so the problem is just given a set of points, endpoints in R2, and you're given weights on the points, and you'd like to find a convex set that maximizes the sum of the weights. So the weights are positive or negative. So this is just a small example, a set of points with a weight attached. And here's a convex set. So the weight attached to this convex set is 5 plus 2 plus 3 plus minus 2. It's not the optimal set, because you could throw in this 0.1 as well, and then we could get a bigger value. But we can maximize or minimize as you like. So that's the problem. It's known to be easy. And the question was, can we find a nice polyhedral description? And so that was it's a sort of a starting point, I guess, for the problem. Okay? In one dimension, it's trivial. You're given a set of points on the line. Take an increasing set of such points. Let's say zi is equal to 1 if xi is in the convex set, which is now just an interval. And it's well known that if you take alternating plus minus with an increasing sequence of points, take any such odd sequence and you write down all these inequalities, that gives you the convex hull in the original space. This comes up in switching machines on and off. It's a standard. It's a fairly well-known result. And so the question is, seem natural. These alternating inequalities seem very natural, and one thought, maybe this is what you need in 2 dimensions. And so that's what we tried to first thing to do. But it turns out, first thing when you look at the problem is that, in fact, it seems a bit difficult to determine unless you fix the lowest point. So one has to solve n problems in which you decide we fix the lowest point, and we're going to solve each of these n problems separately. So here's an example in which we fix this point 0, so all the other points are above it. And now you get, again, sort of these alternating inequalities. As soon as you see a sort of W pattern of some sort, you can see that if I take Z2 and Z7, then I also will pick up Z3. And similarly, if I take 7 and 9, I'll pick up 8. And so you get these inequalities again. But it turns out that they're not facets. There are lots of other inequalities you need. Things seem very complicated. Yes?
So you said that it's easy to find the maximum weight convex set. Can you remind us why?
Well, you'll see in a minute. Yeah. There's some papers. The DP algorithms exist to do it, and we'll come to that in a minute. Okay. And we'll sort of use it. I mean, in a sense, I'll just show you the DPs, Okay. So what we're going to do, instead of working in the space of the points, a natural thing to do is to think about working in the space of the edges. And so now we've got, again, a base point. So now we're looking for an optimal convex set containing this point 0. And now, once we've got fixed 0, we can order the points by their polar coordinates. I've probably got it the wrong way around, but 1, and then we go around clockwise. We come to 2, then to 3, then to 4, and 5, 6. So we put them in clockwise order in some sense. And now, once we've ordered the points in this way, now if I pick up edge 2, 6, for instance, I clearly will pick up 4, which is inside that triangle. And so now I can attach a weight CP to edge PQ, which is the sum of the points in the triangle, where you take into account that you don't want to count points twice, but that's easily done. And so you associate an edge with each edge or each arc PQ. Now you can associate the W's inside the associated triangle. And now if we can find a maximum weight path from 0 and back to 0 again, we're going to have an optimal solution of the problem. And so this is, so we thought, now let's try to think about a formulation in the space of the edges or the arcs. Yeah, because of its ordering, each arc goes from I to J, where J is greater than I, so it's a directed graph. It's become a directed graph. Yeah, it's acyclic. Yeah, because it's because of this ordering now, every arc goes from a smaller value to a higher value. And so now, once we've done things this way, we can say, well, the only problem is that we want the convexity, so an arc PQ can precede an arc QR only if it satisfies an obvious condition that you're turning the right way. And so now the problem we have is just a dynamic program in which we just have to make sure that going from P to Q to R satisfies the convexity constraint. And we immediately get an n-cubed algorithm in this case. And now if we have to fix n different origins, we get n to the 4th in total. And then having got this far, then we found that there were better algorithms for this particular convex set problem proposed by first Epstein and others, in which they wanted to find k-gon, so they fixed the number of points in their convex set, and they had a factor of k, kn squared and kn cubed, and then this later paper they just showed if you drop k, then you get 10 squared and n cubed. And it's a sort of DP recursion, but working just directly on the weights. And so, well, we said, well, okay, so, but still, let's try and write down the IP in the arc space and try and understand what we get. And so this is now just the natural thing we have. We're just sending a flow of one unit from the origin back to the origin, essentially, or back to node n+1, which is at the same spot. And then we've got this condition of compatibility, the convexity condition, on successive arcs. And so, well, natural thing to do now is to say, well, what sort of inequalities do we need to add to get compatibility? We'll get convexity. And then convexity obviously leads this condition. I should perhaps, is that chalk? So essentially, so now if we just take some point Q and we look at the other points, and this is the origin, we've got arcs before and after Q. And obviously, if you can go, this is permitted, then this is also permitted. So anything beforehand, you can go to the same arc. And you can also go to anything coming afterwards. So if this permits this, then this will also permit this. And so you get a very natural convexity, gives you a very natural inclusion on the sets, which the details don't really matter. But it gives you a condition, and it gives you some obvious valid inequalities. If you go from, we're going to order, sorry, we're going to order these points before Q, again in clockwise order, I1, I2, I3, or I1, I2, I3, I4, and we're going to order the points after Q, J1, J2, J3, J4, and you get natural inclusion conditions. So if you can go from IK to Q to JL, and you can't go from IK plus 1 to Q to JL, then it tells you that if you use you go from Q to JL, then you have to use one of the arcs. If you go to here, then you use one of the arcs coming before to get there. And that's all that this inequality says. And then you can obviously strengthen this inequality by, once you have this arc, you can actually add in the arcs coming before it, which are successors. And so you can strengthen the inequality, and you get an inequality like this. And so now, being someone who likes playing with the integer programs, I started adding some of these inequalities, cutting off the points you have. And what happens is that you keep getting integer solutions. So you just take a random selection of these, add them on, and you're always getting still integer solutions. So you've got your shortest path, your longest path problem, plus these additional constraints, and you're still always getting integer solutions to your LP. And so what's going on? And this is just explaining why the problem falls apart in some sense. Here's our picture again of Q. We've ordered the predecessors of Q, I1, I2, I3, I4. Here we've ordered the successors of Q, J1, J2, J3. And now you can just, at some stage, we realize that you can just break up the node Q into now a different set of nodes, into 3 nodes in this case. And so arcs Q1 and Q2 allow you to reach all possible successors, and arc Q3 only allows you to reach Q2, J2 and J3. So from here we can go out by J2 and J3, and I4 we can only go back to I3. And so now the problem has just been broken up. It's now just a pure shortest path problem or longest path problem in this enlarged graph. We do this for each node, and we just get so now the whole thing is just decomposed into a longest path problem on a different graph, a larger graph. And so it's as I said, it's too easy. Perhaps we should have recognized this immediately. And so now these are the shortest path constraints with these new S were just the linking variables between the new nodes. And then to get back to our original problem, in the original variables, if node Q is in the convex set, well, we actually just have an equation that allows us to get back into the original space, because if we've got a P and a Q and our origin somewhere, and then a P arc, P, Q, sorry, R, and now Q, if Q is somewhere here, either it's outside, so if this angle is 90 degrees, so if now P of R is in our path, just looking at the angle of this angle is less than 180 degrees, then we know Q is outside, and if it's just telling, depending on this angle, we can tell whether the point is inside or outside. And so that just gives us this equation in blue. And so now we can get, if we knew how to project this, we could now get back into our original space But that's, and so that's, as I said, a problem has just fallen apart. And so we're still worrying about, we'd like to now extend this to unions of convex sets and see, I mean, there are things we'd like to go a lot further, but we haven't really had any time. And just to go back to the original problem, the alternating sets, 2 dimensions doesn't seem to be the right extension, but one gets but partial orders obviously are. If we go to partial orders and call a set obviously convex, if it satisfies, and it's an intersection of an up set and a down set, and there it's very easy to show that alternating inequalities for odd set, increasing sets are exactly what you need to get the convex hull again. And you can get, so you just need non-negativity and the alternating inequalities. If you take any increasing sequence of points of odd length and then use these. And it also, you get a very simple ON extended formulation and a linear time separation algorithm for these inequalities. So somehow this seems to be the right extension to get, if you're really just interested in these alternating inequalities. So I guess that's all I have to say. Thanks very much.
So questions? So in higher dimension it's hard?
Yes, it's hard in higher dimension. Yeah, they're right. The results of Maurice and other people have shown that already, yes.
And then approximate formulation?
Yeah, I don't know. Nice.
Do you know what the projection of this looks like in the original variable?
Well, no, that's where we started. We had these some of these alternating inequalities, but then you find that they have you can lift in all sorts of other variables, and you get, no, it looks a mess. That's why we went to the arc variables, yeah.
Actually, slightly confused. Sort of one thing. Is this problem generated in the previous problem?
Not really. Just in terms of you can have arbitrary weights on the arcs, and you can have different conditions. Convexity, you can have other conditions than convexity as long as you have this embedding of the successors. You have this property, and so you can imagine sets where you allow not 90 degrees but 150 degrees, or I mean, you can change things. The DPs they only worked on the points in the convex set, but it's really just it's a longest path problem, and with any arbitrary weights, if you like. It's not really more general, but I mean, it's a little bit more general, but it's not. I don't have other applications, put it that way.
So the formulation still requires the fixing of the first vertex, right?
Yeah. That's.
Do you see any hope for doing something without having sort of linear formulation?
Why? I mean, there's just the stupid thing of just taking the union of polyhedra, but that doesn't really give you anything. It makes it even worse. Yeah. Well, I guess I haven't gone back to that question. I don't know.
Because then also one thing is there any likely min-max there, possibly in that thing?
Sorry?
It would still be interesting if there was a min-max there, which you don't.
Yeah. It's not, well, don't know.